Okay, so welcome everybody to this new session of the Severo Seminar course. Today we are very pleased to have with us Professor Chang-Ock Lee. Professor Lee is working at the Department of Mathematical Science in KAIST, Daejeon, South Korea, since 2007. He's also a General Council member of the International Association of Computational Mechanics since 2017, and a member of the editorial board of the Journal of the Korean Mathematical Society. He's also director of Global Institute for Talented Education in KAIST during the period 2017-2019. And Professor Lee today is going to talk us about a dual-primal finite element tiering and interconnecting method for nonlinear variational inequalities using linear local problems. Professor Lee, when you want.
Yep. Okay. Thank you for your introduction, and also thank you for your invitations to the seminar on SIMNI. Okay, my talk title is Dual-primal finite element tiering and interconnecting method. The abbreviation of this method is called the PETDP, and it's about the domain decomposition method. So that's the domain decomposition method for nonlinear variation inequalities using linear local problems. Actually, this work is performed with my the postdoc, Jong-Ho Park. Okay. Yeah. So first, let me introduce the my model variational problems, the variational inequalities. So suppose that we have a bounded polygonal domain first, and then we can consider a overlap space. So with this H1 overlap space, but on the boundary, okay, on the boundary we have the Dirichlet conditions. So if you have this domain omega, then on this, say, this is gamma d, then we have on gamma d, this function is 0. So this is very standard usual overlap space. And also we introduce some Hilbert space Z, and we introduce a bounded linear map from that V to a Hilbert space Z. So we have a linear operator A, and now this plays a role of some constraint to the variation inequality problems. So let's see model problems here. So model problem is first we consider the this bilinear form, and this bilinear form is now greater than or equal to that the function f here. Okay, so u v minus u is greater than or equal to f v minus u for any v in that space v, but our restriction constraint has this lv is in k. Okay, so also solution mu is in v, and that is also satisfies lu in q. Okay, so okay, just a moment. Okay, yeah. So so in simple case, A is just a bilinear form like that. That means it comes from Poisson equations or Laplace equations. Okay, so that is very standard way. And let me introduce some examples of two variation inequality models. The first one is obstacle problems. So we consider the linear operator is just identity, and G is the same as V. So we have the identity is this mapping from V to G, and actually G equal to V. Okay, so our constraint is K is now you have that. So the solution mu should be below than a given function gu, and it should be above than gl. Okay, so that's our constraint. And so in that case, k should be non-empty also. So in this case, our problem is called the obstacle problems. Okay, and another example is the contact problems. The contact problem is now we have a contact boundary. So contact boundary means here we have a boundary is here. So say this is gamma D, and if gamma C is here, okay, for example, here this is gamma C, okay, then we have this gamma C is, actually we have G is the trace space of V on gamma C. So here the operator L, linear operator L, is just the restriction operator to the gamma C. So our constraint is here, this. So U is in Z, but U is greater than or equal to GC, okay, on gamma C. So we're gonna find the solutions of the previous problems, but the solution must be greater than, above that given GC on that contact boundary. So this is called contact problems. Okay, we have contact problems here. So now we try to have the equivalent problems to that the variation inequality. So the variation inequality is actually we find the solution of this problem. So we have minimization problems, but it should satisfy the given constraint. So we apply here, we insert this term here. So here the chi k is, we call that is the indicator functions of k. So chi k is, if w is in k, then it's 0, and w is not in k, it's going to infinity. Okay, so if you see these minimization problems, LU is not in k, then LU is not in k, then it goes to be infinity. So in order to minimize these, LU must be in k. So if you consider this problem, you can see this is exactly the same as our previous variation inequality problems. Okay, so we're gonna minimize these functionals. Okay, so we minimize these functionals, but we have a constraint here. Okay, so we have that conditions, and now if you look at this is nonlinear minimization problems. Okay, so due to these constraint terms, it becomes nonlinear minimization problems. And now our goal is we develop an efficient iterative substructuring method. Okay, so let me say what is the iterative substructuring method first. So suppose that we have a domain omega here, then we take the partitions of this domain omega into several subdomains. Okay, so that process is called mesh tearing. And after we tear the meshes, okay, so we have partitions of subdomains, then now we connect the solutions of the problems in each subdomain by using Lagrange multipliers on the interface. Okay, so this is called mesh reassembling, or the so that this is called mesh reassembly. Or the here, if you look at the method, you find the element, the tearing and interconnecting. So we say this process is reassembling or interconnecting. So so the idea of a domain decomposition method is we solve the problems on each subdomain separately, then there is a difference of solutions on each interface. So using the Lagrange multiplier on that interface, we try to match the solutions on the interface. Okay, so we just try to match the interface solutions. Then we solve the subdomain problem again to compensate the difference in the interface. Okay, so we repeat that. So we find Lagrange multiplier. Using that, we solve the local subdomain problems, and then we update our Lagrange multiplier on interface. Then again, we solve the problems on the subdomain. Okay, that's called the iterative substructuring method. So we're gonna find the efficient iterative substructuring method for the nonlinear variational problems. Okay, so here we want that our domain decomposition method should be applied to nonlinear problems itself, not the linearized problems. Okay, so the very basic approach is we linearize the nonlinear problems, and we have several good methods for the linear problems. Okay, that's a very standard way to solve that the variation inequality problems. But here, instead of that, we apply the domain decompositions to the nonlinear problems itself, and we design nonlinear domain decomposition problems. And one more thing we want to that is we don't want to have floating point subdomains. Okay, so suppose that we have several subdomains. Then, for example, this domain is connected to the original boundary, but if you look at this part, okay, if you look at this part, then this domain is not connected to the original domain. So we call this as the floating subdomain. Okay, so if you see the previous the petty method, okay, so this produces floating subdomain problems if you have more and more subdomains. Okay, so we won't remove this floating subdomain problems. So instead of petty method, we apply the petty DP method. So let me say what the petty DP method is later. And also we want no inner iterations. No inner iteration means, okay, so I already told you that we solve the subdomain problems and we update Lagrange multipliers on the interface, and then we solve the subdomain problem again. Then we update Lagrange multiplier in the interface. We repeat that, and in solving the subdomain problems, we want that our method, okay, can solve the problems directly in subdomain case. Okay, so the subdomain problems should be linear problems, and we solve the problems by a direct solver. Okay, the next thing we want is the method is linearly convergent with the rate better than the existing works. Okay, so the existing works, the best of existing works is developed by Dostal, and it adopts the petty DP method, and the convergent rate is 1 minus R, and the R is some positive real number which is less than 1, okay, but less than 1, and it's proportional to the condition number of dual operator. And in this case, if R is close to 0, then it's almost 1. And in this case, we developed that the problems, okay, 1 minus square root of R. Okay, so it's the convergence rate is better than that. Okay. So now let's see some finite element discretizations. So if you are familiar with the finite element discretizations, okay, yeah. So I want to skip here, but if you are not familiar with this finite element discretizations, we can review very, very briefly. So it's our solution space, and we consider a quasi-uniform triangulations of omega, and we take some finite dimensional space. So we take the piecewise linear functions, okay, locally. So on each triangles, we consider the the piecewise linear functions. So we call this is a piecewise finite element space. And also we assume that the some suitable discretizations ZH, KH, LH. Okay, so we have the function space G, K, L. Okay, so our solution, so the L is from B to Z. Okay, so we take some discrete approximations of these. So in this case, in general, our ZH is chosen as the m-dimensional space, and here m is the number of pointwise constraint, and our assumption is KH is a closed convex subset of Z. So usually we take that. So, and the finite element discretizations of this variation inequality model is now, so instead of continuous problems, we replace each variable, by the discrete variables. And that each function is in the finite element space. Okay, so so under appropriate conditions on these space and operate, if you choose a very, very suitable one, then we have this, the finite element convergence. The convergence is OH. So we have the first order approximations. Okay. And now we consider discrete version of minimization problems. So now we consider minimization of these problems in discrete space. Okay. So that the bilinear form is now expressed as some vector functions and the matrix. Okay. So we can write that the same thing is this. So we're going to minimize these functionals, and this first part is very standard in elliptic, PDE, and this is now, this is nonlinear terms, So the LH, UH is in KH, then this is 0, and otherwise it becomes infinity, So we're going to minimize this functional when UH is in VH. Okay, so now our assumptions. So let me give some assumptions and notations. First, we consider the n non-overlapping polygonal subdomain. Okay, so we have omega here, then you take some partitions, and now each subdomain is called omega k. Okay, so so omega is divided n non-overlapping subdomains, and now maximum subdomain size. So this size is capital H, maximum subdomain size, and each omega k is now union of cos triangles of global conforming mesh. And each cos triangle is a union of a fine triangle. So if you magnify this one, say this omega k, then again you have a meshes here, and so you have a triangulations here. So THK is a triangulation of omega k, and so the k is the index for the subdomain, and the h is the index for the the size of the mesh. So if THK and THL have a common nodal points, then we have the interface. So the interface is denoted by KL. And now here we consider the space WK. WK is now continuous and piecewise linear finite element space in omega k. So in omega k, so in subdomain omega k, we consider that WK is piecewise linear finite element space. And now we take just the product of this WK. So this is just a Cartesian product. So if you take the partition, the subdomains, then you can think each the subdomain is separated. So you can consider these separated subdomains, and each one is called WK. So just this is a collection of these subdomains. So that is W. And now you put the continuity. Okay. Now you put the continuity on the interface, then that is called the W hat. Okay. So the function is defined on each omega k, and if there is a continuity on the interface, then it's a W hat. Okay. So now RK is a whole finite element space to the WK. So this is called the local restriction operator. Okay, this is called the local restriction operator. And now R is now from VH to W hat. Okay, it's called natural isomorphism. So if you consider VH is actually continuous functions, right? So you have take RK is now restriction to the WK, and you just collect all of these, then it's automatically continuous because the originally the UH is continuous. So okay, so the R is called that. And also we have D. D is called the diagonal scaling operator. So it has only diagonal entries, and the diagonal entry is equal to the 1 over n0. Here the n0 is the number of freedom, okay, at that point. So if you have if you have, okay, this case, in that this point is the interface that shares two subdomains. So in this case, n0 equal to 2. And if in this case, okay, at that point, n0 is 4. Okay, so we have that the diagonal scaling element. And now, so we can write that already know that this bilinear form is expressed as that the matrix vector product, and also we have FK, and now we consider the matrix A. This is a blank matrix, and its diagonal element is A2, A1, AK. Okay, so actually this A1, A2, AK are stiffness matrix on each subdomains. So we have A is that, and now you consider the operator AH. Operator AH is now this RK. RK means restrictions to the WK, okay, restrictions to subdomain, and this AH is a subdomain stiffness matrix, and now take a transpose of that. So this is now the result is belonging to the VH, okay? So we take a sum of that. So we have also the FH here. So now we define the linear operator L, okay? So now from the discrete space to discrete space, and we define L as this. So we have a scaling operator, and the restriction, R is restrictions. So we have transpose over that and the LH, okay? So our, okay, our energy functional is, okay, discrete energy functional is that. So here, okay, if you consider RUH here, then we have that. So actually this is just the notations for discretizations. So now we consider the degree of freedoms of W. W is actually just a collection of, okay, finite element space on each subdomain. Okay, this is a collection of finite element space on subdomains. So in this case, we have two subdet, okay, the capital pi and the delta. So capital pi is called the primal variables, and the delta is dual variable. So if you consider these, if you consider the intersection of two subdomains, okay, then in fact, DP method, we put the cross points, so corner points, as the primal variable. So these are denoted by this. And the delta is the interface variable. Okay, so that is called the dual variable. So now we define W hat, W tilde. Okay, we define W tilde. That is a collection of all functions in W that is continuous at the primal variables. Okay, so we have a subdomains, and the W is just a collection of these. And if the functions are continuous at these points, okay, if this is continuous, then this is called W tilde, and the continuous and whole interfaces, that is called the W hat. Okay, so we have W, we have W tilde, W hat. Okay, so W is just a collection of subdomains, the finite elements, and the W hat is continuous functions. So subset of W, but the continuous at the primary variable, and the W hat is now subset of this and the continuous at the every interface. Okay, so now we assemble those things. So from the W, okay, from the W, if you consider W tilde, okay, this is called the assembly operator. So you have a function on each subdomains, and now you try to make the continuous functions. Okay, so you consider first, okay, this restriction operator. Okay, for the continuous functions, you have restriction operator to, okay, so this W tilde to W. So from the continuous functions, you restrict the functions into each subdomains, and you take the transpose of that, then you obtain the primal assembly operator. Okay, so also the continuity of dual variable is imposed by linear jumper operator. Okay, so jumper operator is now, say, if you have two variables, so at the same point you have two function values, ui, uj, then bu is ui minus uj. So this is called the jumper operator. Okay, so this means that the for the continuous functions, okay, so W tilde is continuous at the primal, okay, primal load. So the continuous at the primal degree of freedoms, primal variables, but on this interface, this is discontinuous. So in this case, U tilde is in W hat. W hat means this is continuous. That means its jumper is 0. Okay, so we have that. So using these operators, we write again our functionals. So our minimization functionals here. Okay, so we have that, and now A tilde is, okay, A tilde is now, okay, restriction operator to the primary variables, and this restriction to the that, and we consider A, the A operator, and we take a transpose. So we're going to minimize. Actually, our problem becomes that. Okay, so we're going to minimize this E tilde, U tilde. Okay, we minimize these problems, but the solution is in W tilde. So W tilde is what? This is now continuous at primary variable. So if you have these four subdomains, then it's a continuous at these corner points. Okay, this should be continuous. So you regard that as one point. So sometimes we draw these pictures like like that. Let me see. Yeah, draw this picture like that. Okay. Okay. So these corner points are attached. So it has one variable. Okay. And in this case, these points are physically the same, but it has two function values because we separate those. So we apply now we consider, so here, so in the interface, jump operator should be equal to zeros. Okay, so in order to have this condition, this constraint, we put that constraint into this minimization function. Okay, so again we have the indicator functions. So u tilde equal to 0, then this function, this is 0, otherwise it becomes infinity. So we write that as this minimization functionals. So now we're going to minimize this. Okay, so here now, yeah, so this is just the notations for that. So actually we have, this is our standard, the elliptic problems, and we have two indication functions. Okay, we have two indicator functions. One is, okay, the indicator functions to make the solution satisfy the given constraint. And this is now, it's okay, this is constraint to make the jump be zeros on the interface. Okay, so we consider those here, and we consider those here. So now we consider Legendre-Fenchel operator, Legendre-Fenchel conjugate. So for this operate, it's very easy to find the Legendre-Fenchel conjugate, okay, with these forms. And for this case, we need some manipulations because this is not the standard. Okay, so yeah, because this is not the standard functions. This is nonlinear functions. So we have from the nonlinear functions, we can make this Legendre-Fenchel conjugate of that. So now using the Legendre-Fenchel conjugate, okay, we have the dual problems, and the dual problems becomes that. Okay, so now dual problem is about, okay, only the lambda and the mu. Actually here, lambda and mu is called the Lagrange multiplier. So we have this Lagrange multiplier, and we're gonna minimize these functionals in terms of Lagrange multiplier. So this is dual problems in the sense of Legendre-Fenchel. So this is called the Rockafellar, the Fenchel-Rockafellar dual problems. So we're going to minimize this one. Here again, we have the Legendre-Fenchel conjugate. So there is primal dual relations between dual variable and the primal variable. So this Lagrange multiplier is regarded as dual variable. So primal variables now can be recovered using these relations. So our problem is domain decomposition problems for the nonlinear minimization problems. So we solve here, okay, here, yeah. So if you find this Lagrange multiplier on the interface and also Lagrange multiplier for the that constraint problems, then you can recover our solutions easily from the primal dual relations. Okay, so now we denote this as gamma bar, this as p bar, and this is our f bar. Okay, so in our problems we have two the important assumptions. One is now we have a KH operator, right? KH operator is actually, this is what, the BH2GH. Okay, so yeah, so the KHU must in Zn, right? So this is restrictions. So we have that restriction space. Okay, we need some projections to that restrictions. So this projection has a closed form formula. That's our assumptions. Okay, so yeah, for the W, okay, for the Z, okay, for the Z, you're going to find the W in that KH. Then if it has the closed form formula, okay, you can do more. So that is our assumptions. And another thing is the minimum eigenvalue of the matrix D. So L is actually this is V2G, right? So this is about the constraint also, okay? So this LH transpose computable bound. So the minimum eigenvalue is a computable bound, okay? That means the minimum eigenvalue of this is some number CLH, and our assumption is we can compute that minimum eigenvalues, okay? And also we need some proximal operator, okay? So proximal operator is we have a function gy, and at x, okay, at x we have this quadratic functional, and we're gonna minimize this, okay? So we have z, and okay, at the x we have a quadratic functions like that. So this is called the proximal operator. Proximal operator. This is a very standard operator in mathematical optimizations. So using the Morrow's identity, our first assumption is that here that projection operator has a closed form formula. Then we can calculate this proximal operator as these forms. And the projection is now, assumption is projection has a closed form. So this means this proximal operator has a closed form formula, okay? So from the assumption that the projection has a closed form, we can calculate proximal operator using closed forms. Now, our lemma 1, the first lemma is minimum eigenvalue of f hat is this one. So you can compute this one, okay? So f hat, right? And here CLH is now minimum eigenvalue of the minimum bound of low bound of this minimum eigenvalue. And our second assumption is we can compute this one, okay? So second assumption is we can compute this one. So, and our algorithm is now here. So for the F bar, okay, so the F bar is here, right? F bar is here, and the B is a jump operator. A is the stability matrix, okay? So our assumption is we can compute maximum eigenvalue of this by power method. And also, you can compute the maximum eigenvalue is A tilde by Gaussian circle theorem, okay? And then, since we know that the maximum eigenvalue of this, okay, since we know that the maximum eigenvalue of this, we can calculate the tau, okay? And also we can calculate alpha, because we can calculate the maximum eigenvalue of this one, and we know that the CLH by the assumptions, and then we have initial Lagrange multiplier for the interface jump, and this is the Lagrange multiplier for the Lagrange multiplier for the constraint, and we have these algorithms, okay? So we have a Tn, we define beta n, and we update Lagrange multiplier using this lambda hat, and also you update that, and finally you obtain these lambda m plus 1 and mu m plus 1. Okay, so in getting lambda, you need to solve a tilde. Okay, so that is used as a right-hand side and solve this problem. So this is linear problems. So this Lagrange multiplier on the interface and for the constraint, and each step you need to solve subdomain problems. Okay, and here also you need to solve subdomain problems here and take the proximal operator. So since this proximal operator has a closed form, you can easily compute this part. So this is our proposed the PTDP method for nonlinear, the variational inequality. So our lemma 2 is maximum eigenvalue is now below, has a bound, constant bound. And so using that, we can see minimum eigenvalue of f hat is bounded by that. And also we consider the set delta prime, which consists of some degree of freedom of W tilde. It will be determined by the target problem. So that means it will depend on how you choose the some degree of freedoms according to the problems. Now we consider S delta union delta prime. It's called the Schur complement of A tilde. Okay, we eliminate the degree of freedom other than that. Okay, so then we have maximum eigenvalue of f hat as that. So here we know that this LH transpose, and actually we estimate minimum eigenvalue of this one. Okay, so we have a theorem 4. Now we consider some estimations. Okay, we consider the functional estimations. So this is a minimum, and this is actually greater than the minimum value, and this is below than that. So when this minimum eigenvalue is 0, so that the CLH is 0, then we have this case. And in most cases, minimum eigenvalue is positive. So in this case, CLH is positive. So in this case, we have estimations like that. So from that, you can see this has linear convergence, and the convergence rate is 1 minus square root of Q. Okay, and the Q is depending on this. So low bound of Q is this. So the minimum eigenvalue of that Schur complement operator, and the maximum eigenvalue of this one. Okay, so now the corollary is, okay, at each iterations, okay, the primal solutions and these dual solutions has these relations. So from that relations, we have the error estimate. So that error estimate is now it's bounded by these terms. So also, so this means it shows that linear convergence. Okay, linear convergence, and the rate of convergence is 1 minus square root of 2. Okay, so let me get back to our obstacle problems. In the obstacle problems, okay, we have these GH and the VH, and the LH is so identity, and our constraint is that. So solution is greater than or equal to GL, and the solution is smaller than GU. Okay, so in this case, we can easily get the projection operator. So projection operator as this closed form. Okay, so our assumption is if the projection has a closed form, then our assumption is that, and then we can write proximal operator using this closed form of a projection operator. So you can get the you can have closed form of this this proximal operator. And since the LH is identity, all eigenvalues are 1. Okay, so by these assumptions, CLH is 1. So in this case, we consider delta as all degree of freedoms. Okay, so in this case, sure complement is equal to that. So we can calculate minimum eigenvalues with that. It's H is mesh size of the original finite element space, and the capital H is subdomain size. Okay, so using that, we have now the convergence rate is 1 minus root q, square root q, and the q is this q has the bound of that. So it depends on h square and that. Okay, so now you have this finite element discretizations and this subdomain. Okay, and we have this as a primal variable at each corner point. And here now we have this is the functions constraint below and this constraint above. And the solution is then now this. Okay, so this is a constraint above, this is a constraint below. I mean, this is a constraint, actually constraint below, this is constraint above. Okay, so you can get these solutions, and it shows there's some iteration numbers and maximum eigenvalues over that, and this is time. Okay, this is time for using the parallel computers. Actually, we use the parallel computers with the number of cores, which is equal to the number of subdomains. Okay, then we have very quickly we can solve the problems. And again, we have now contact problems. Contact problem is we have a contact boundary. So in this case, now we have this is a constraint. So u is greater than or equal to some function gc. And in this case, we have this projection operator has a closed form. So using that, we have you can find the closed form of this proximal operator. Okay, so we have a very similar one, and now we put that. So the Dirichlet boundary is y equal to 1, and the contact boundary is y equal to 1. And here the f equal to 0, so we can find some harmonic functions, and this is the functions on the contact boundary. So here, this is y equal to 0 here. Okay, so y here y equal to 0, and here this is a contact boundary y equal to 1 over 4x plus 1. Okay, so yeah, I mean solution f. I mean the solution f here. Okay, yeah, I mean solution. Yeah, so you can solve their problems. Okay, so this shows there's some iterations, and okay, for several h and small h, capital H, and we can solve it very quickly. So using the parallel computers here. Okay, so this is also the numerical comparison with given previous existing works. Actually, existing works, the convergence rate is 1 minus q, and in our case, it's 1 minus square root of q, and so q is 0 and 1, so it's much better. Okay, this is so it shows that in our case, for the several small h and the capital H. Okay, so let me have some conclusions. We proposed a dual-primal iterative substructuring method for nonlinear variation inequality, and although target problem is nonlinear, the proposed method linear local problems which can be efficiently solved by direct solvers. Okay, and while existing works on iterative substructuring method has been concentrated on the contact problems. Actually, Dostar algorithm is working on the contact problems, but our proposed method is working on the more general problems, so contact problem and contact problem and the obstacle problems. And also we proved that our proposed method has improved the linear convergence rate, 1 minus square root of 2 square root of q, and the Dostal algorithm is 1 minus q. Okay, thanks for your attention.
Thank you very much, Professor Lee. We have a short time for some comments or questions, if anybody wants to ask. I had one curiosity. This Dostal method, what is it based on?
Yeah, actually, this is also the based on the PETI-DP method, but it's not used as our approaches. Our approach is now that our approach is actually we transform our problem into the dual problems. We consider the dual problems and we minimize the dual problems, but the Dostal just approaches as the primal problems. That's
that leads you to a better convergence rate.
Yeah.
Right. Okay, that's good. And which platform? Well, Alex Ferreira is going to ask afterwards, but I was wondering which platform are you using to code this? Are you using MATLAB or?
Oh, the coding is just a C.
C.
Yeah.
And
C.
is it an existing software or is it just?
We don't use any existing software. We just decoded everything using C. Okay, and also the MPI in Linux machine.
Yeah. Okay, great. Alex, please go ahead.
Yes. Hello, Professor Chang. Just I want to thank you for your presentation, and it was very interesting. This convex optimization approach to domain decomposition and contact problems. I wanted to see if I understood well. Is it just doing this method is like doing like a proximal dual point with and instead of acceleration method?
Yeah. So if you consider the Fenchel duality, then we can convert it to the primal problem. We can convert the primal problems to the dual problems, and in that case, you can easily apply the primal dual algorithms and the dual algorithms. Okay, so actually, there is very nice algorithms in mathematical optimizations. So we adopt those things. Okay.
Yes. But
then in the calculation of that, we need the proximal operator, and the closed form of proximal operator is very, very essential to actually calculate.
So the rate that is improving is because of the instead of acceleration, is it? The method, the thing that is increasing is because the rate is being better is because of the acceleration of this beta and t, right? I am getting it right?
Yeah, right. Yeah.
Okay. Okay, thank you.
Thank you, Alex. Thank you, Professor Lee. Is there any other short comment or question? If there are no more questions, I think that we can close the session here. Thank you very much again, Professor Lee, for this nice presentation. And see you all in the next session of the Simulation Seminar course.
Okay, thank you very much. Okay.